we heard a lot of excellent talks earlier today that reminded us that about the importance of providing safe and reliable access to clean and affordable water, and how technological innovation as well as novel approaches to think out of the box are extremely important. And today we have three excellent talks that are going to represent this and hopefully move us towards sustainable integrated urban water management. Our first speaker is Markus. He's the general manager of the Orange County Water District. He has over 30 years experience with water utilities and as well as with water resources management. And he is an expert in groundwater replenishment, and he's going to tell us about what they're doing about that. So please help me welcome Mike.
Okay, we'll see if we can get this. Okay, looks like we're ready to go. Anyway, thank you very much for the introduction, Pedro. And the one thing I'm not going to talk about today is GWRS. You know, my kids accuse me of being a one-trick pony, only knowing, being able to talk about the project. And I've already had several people outside say, I hope you're not talking about GWRS. So I won't do that. However, what I do want to talk about is maximizing performance of surface water recharge facilities to sustain groundwater basin yield. And just as an introduction, the Orange County Water District is actually a groundwater basin manager. So we oversee this huge groundwater basin we have in North Orange County. And it becomes a source of supply for the cities that overlie the basin. In fact, this year we provide up to 68% of the total water demands in our service area. And being a non-adjudicated basin, our board of directors can change the pumping every year. Every year in April, they change the amount of pumping that can be pumped out of the basin. So it is a very actively managed basin. We are in the bottom of the Santa Ana watershed, so we form the lower Santa Ana watershed. In the upper Santa Ana watershed, you can see it's much larger than we are. We get a large source of our water for recharge from the upper watershed, however. All of the cities up there, most all of the cities, discharge their wastewater into the Santa Ana River. And it flows downstream, collects behind Prado Dam, which is right at the confluence of the three counties, and then comes down into Orange County. We capture it in our recharge basins, and then it becomes a major source of supply for the groundwater basin. Another thing that we do is we capture a large amount of storm flow. As I mentioned, also I mentioned Prado Dam, and Prado is right down here. And we have agreements with the Army Corps of Engineers to hold stormwater behind Prado Dam. So during the winter, we can hold it at a certain elevation that would allow us to capture 9,000 acre-feet of water. And then in the spring and summer, it goes up, which would allow us to store an additional 10,000. So we're actually actively working with the Corps to try to allow us to store more water during the winter when it's available, so that we can use that as a source of recharge. However, the wastewater is high in nutrients and the stormwater is high in TSS. As a result, our basins have a tendency of clogging, so we have to drain them periodically, dry them out, mechanically clean them in order to restore the recharge rates. So we're looking at ways in which to desilt that river water so that it can percolate at a more sustainable rate. Recharge is central to sustaining groundwater basin yield. There's different types of water that we get, natural or incidental recharge, which is rainfall or subsurface inflow, and that's just water that flows our rainfall that occurs outside of our recharge basin that then percolates into the groundwater basin. Injection well recharge. We have a seawater intrusion barrier in Fountain Valley to prevent seawater from coming inland and contaminating the groundwater barrier. We currently inject anywhere between 20 million gallons to 35 million gallons into that recharge basin, our recharge barrier. In the future, we are developing a project called mid-basin injection, where we would take the highly purified GWRS water and inject it into the middle of our basin where there's a clay layer near the surface. So we'd pop a hole through the clay layer, inject the GWRS waters, and put it in a place where the basin has a very large overdraft. So there's kind of a pumping depression in that area. By injecting the water mid-basin, we'll hopefully be able to fill that up a little bit to take care of the groundwater levels in that area. There's also in-lieu recharge, and this happens when we purchase treated water from Metropolitan and then turn our pumps off. So it's a means of artificially keeping the groundwater level high by purchasing water from Metropolitan. Surface water recharge, and that's only possible in the Anaheim and Orange areas due to the geology. There, and again, the sands and gravels come up near the surface, so you just have to dig a little hole, and you're connected directly down into the groundwater basin. And this shows a very old picture of our recharge areas. If you look closely, you can actually see orange trees. I don't know whether there's any orange trees left in Orange County. Maybe a couple groves in Irvine. But that shows the Santa Ana River in its kind of natural condition before it was channelized and before the construction of Prado Dam. This shows our recharge areas. One of the first acquisitions we had was back in 1936 and 47. And that was a 7-mile stretch of the Santa Ana River between Imperial and Ball Roads. So we purchased that, and then in 1958 we purchased this off-stream basin here. At the time it was called Krill Basin, and built a pipeline so that we could divert water off the river into that basin. And you can see how subsequently over the years we've just added on to those basins. 63 to 68, the Warner Basin right here, followed by a bunch of off-stream basins here, upper lower Five Coves, kind of our off-river system, and then Kramer Basin right here. In 83 through 85, we purchased this very large recharge basin. I think it has a capacity of storage capacity of about 12,000 acre feet. We also built a pipeline from the bottom end of the river at Ball Road over to that recharge basin. And most recently, we've acquired a basin just last year, just put it in operation, Mariloma Basin. So we really have purchased a lot of property over the years for recharge basins. And as a result, we've increased the yield out of the basin tremendously. So we're able to allow our pumpers to pump quite a bit of additional water. And of course, as people came in the 40s, 50s, 60s, pumping demands increased, so we had to increase the yield of the basin. The surface recharge basins provide about 2/3 of the groundwater basin recharge over the last 5 years. So this is a 5-year basin. You can see in the pie chart 67% of the water that is recharged is in those basins that we showed on the previous slide. So those basins are used, as I mentioned, to capture Santa Ana River flows, to capture stormwater flows, and then also recently, over the last 5 years, we've been pumping GWRS water to those recharge basins also. So there's basically 3 types of water that are introduced to those recharge basins. And that's at 2/3 of the pie. Incidental recharge, as I mentioned before, about 21%. In lieu, 3%, and then the barrier recharge, about 9% of the water that goes into the ground. So that big piece of the pie, so those basins are very, very important, and so it becomes very important to keep them percolating as high a rate as possible. Enhancing and expanding the surface recharge system has the greatest potential to increase the recharge. Future expansion of the seawater barrier, we think we can get to anywhere between 3,500 and 9,000 acre feet per year. Mid-basin injection, we're looking at about 2,500 acre feet per year per well site. In lieu recharge, that's kind of being phased out by Met. That probably won't be as big of our recharge portfolio moving forward in the future. And then surface recharge, and this is a very cost-effective method. We can get up to 700 acre feet a year per acre with Santa Ana River flows, which I mentioned are fairly heavily silt-laden, and up to 3,700 acre feet per year per acre with GWRS or Met water, which of course is ultra-pure or drinking water. So that will perk very, very well. Compared with Santa Ana River water, nearly 3 times as much GWR or Met water can be recharged in Miller Basin. Miller Basin is a flood control basin, so it doesn't have real high sustainable perk rates because it's been used for flood control, so there's been a lot of sediment dumped in it. Over the years, that sediment has been compacted and has gone down into the ground, so we don't see huge perk rates there. And it's very hard to see. We use the wrong color for GWRS water, but it's actually graphing right up along here at about 40 CFS average. Met water about the same. It's a little jumpy in here because they turned off for a little while, reduced deliveries. And then you can see Santa Ana River water. It does have a decay, a die-off from about 35, 34 CFS down to 20, and then it goes down considerably after that point. Once it gets to a certain level, as I mentioned, we'll jump in, we'll take the basin out of service, and then clean it to restore that percolative capacity so that it can come back up to the original rates. This shows what Miller Basin looks like with GWR water. It's not quite as dramatic. It really looks like South Pacific Island down there. The very clear water. You can see down to the bottom. You can see the check valves that are submerged underneath there. And the TSS concentration in GWR water is less than 0.1 milligram per liter, so extremely low. Recharge capacity of a different basin. This is Kramer Basin. It has historically taken a lot of river water also. However, it is at the end of the system, so a lot of sediment has fallen out along the way. It has very, very high sustainable recharge rates when cleaned and when using clean water. So you can see with met water, and here we were taking a lot of water all at once, and it got up to 100, and then it starts dying off a little bit. GWR water, the same thing with an extended decay. And then the Santa Ana River water, a very steep die-off. So we can see the benefits of being able to have that GWR water and that cleaner water in those basins, allowing us to have higher and more sustainable percolation rates. Clogging is the curse. Clogging of the infiltration surface and resulting reductions in infiltration rates are the bane of all artificial recharge. And that was Herman Bauer made that comment. And it's true. Clogging is a key constraint in maximizing the capacity of the existing system, and research has shown that suspended sediment is the primary cause of clogging, and OCWD actually developed an empirical formula that confirms this. And the two terms to pay attention to are the flow at time zero, or Q naught, and then L, which is the total mass of solids. So in essence what this equation says is that over time, the mass will decrease the amount of Q into the basin. And this shows how we arrived at that empirical formula. So we actually took data over 3 years and at different times of the year of percolation of Santa Ana River water, there again, this highly silt-laden water, and then put the best fit curve in there to come up with the equation. And we have these decay curves for each one of our basins, so it's a very good predictive model for us to be able to know when we may be able to get in or have to clean basins. So about 5 years ago, we went to our board and we said we think we ought to take a look and research different methodologies that could help restore percolation or take the sediment out of the river water. So we spent $1 million study over the course of a year and came up originally with 5 technologies to try to see the effects of that river water and how efficient these technologies would be able to desilt the water. So they consisted of flocculation, sedimentation, dissolved air flotation, ballasted sedimentation, cloth filters, and riverbed filtration. After the year's study, we ruled 3 of them out as not being effective and came up with the final 2, the cloth filter and the riverbank filtration. So the recharge water sediment removal demonstration projects were both the riverbed filtration and the cloth filter. Our goals are to acquire field scale estimates of increased recharge rate, probability by each method, assess the feasibility of using it at a larger scale, and a testing period of at least 2 years. And it may be more than 2 years. It may be 3 or 4. We have to have enough data because there's such variability in flows and hydrology. We want to make sure that we capture some of the worst case situations along with the best case situations before we do the evaluation and make a decision as to whether to move forward or not. Cloth filter basin was just recently installed at a smaller one of our basins, Riverview Basin. In fact, we just went online in September. It has a capacity of 5 to 8 CFS. The unit has 12 filter discs, so similar technology. I think LADWP uses this in their water treatment facility up in the valley. The discs are cleaned by backwashing, can remove up to 90% of the suspended solids, and is kind of a unique application for what we're doing. So we hopefully will get a lot of real good data on this and be able to see whether it'll be able to help us out in the future or not. Of course, riverbank filtration system takes advantage of natural filtration processes to remove suspended sediments in the water. What we've done here in one of our, this actually isn't the river, but it's called our off river, which is immediately adjacent to the Santa Ana River. So we've excavated, we put in some slotted PVC pipe. We're going to use that sand, in essence, to remove the silts. The theory, if this works, if we put it in the river, is the silts will become more or less self-cleaning. So we don't have to remove or worry about the silt removal or silt disposal. The river will do that for itself. So we've started a project here, as you can see. What you were looking at was the off-river up just below Weir 4 here. And we plan on putting in more of that system, or that passive system underneath here, build a pipeline, take it to this small basin here, and be able to evaluate exactly how effective that should be. And we have really, really high aspirations that this will work. It's a real cost-effective means if it does work, and we think that we'll be able to get very, very high sediment removal out of this system. This just shows a picture of the PVC pipe. We're looking at two different things. As I said, conventionally, slotted PVC pipe is used. We're also looking at these Atlas rain tanks or collector cells. What we do is we wrap it in filter cloth so that the sand couldn't get inside. It has a lot of volume. There's a lot of surface area there for the water to drain into it and collect very high volumes of water. So I don't know that this has really been explored before, so it's going to be interesting to see how it turns out. You can see here where we've excavated in that same area. We have the filter cloth laying the crates on top of it, and then kind of transitioning to a pipeline that will take that water then, as I said, down to this other basin, this Ball Road Basin. So these projects really are demonstration projects, and we've told our board that, and they understand that. You know, hopefully we'll get results out of this. Hopefully it'll lead to more effective silt removal. This shows you what the silt looks like when it dries out. And it's hard to see here, but this is pure sand right in this area. And these chips, they look like little, or form like little potato chips, if you will. When allowed to dry on the bottom of a basin, they will form, and then we'll go in there. And historically, we've gone in there with brute force and awkwardness, in that we've taken D8 dozers, and we've made an attempt to skim 1 inch to 1.5 inches of this layer off the bottom. That's how we've done it historically. We have maybe wised up a little bit. We went with this small beach cleaning device. It's got a little blade down here that skims the chips off and then throws it into a hopper and back. That's kind of a small scale device for a smaller basin. Instead of using the brute force and the D8s, we're actually looking at paddle wheel scrapers now, a little 913 paddle wheel scraper to pick those potato chips off the bottom and then store them on top. Miraloma Basin, that's our most recent basin right down here. Here's Anaheim Lake. Miller Basin, Kramer Basin is empty at this time. But Miraloma, 10 wetted acres. This is dedicated to GWRS water, that highly purified water. There's never been any Santa Ana River water in here. As a result, we expect extremely high percolation rates. And we've seen them. We just started utilizing it. We're putting GWR water up there. We're putting 50 million gallons a day up into that basin, and we cannot wet the bottom of the basin. We're getting such high sustainable percolation rates. So about 18 feet a day, 50 million gallons, 75 CFS. It really is working out outstandingly. It'll enable us also probably to continue to operate GWRS during the winter when so we'll be able to operate it year round instead of maybe having to shut it down during the winter when we would capture some storm flow. So that's an outstanding example of what a new basin can do. And in fact, we're in the market for purchasing more property in the city of Anaheim right now as we speak. So OCWD is committed to maximizing the capacity of the surface water recharge system. Surface recharge system provides 2/3 of the recharge of the groundwater basin, so it is a significant chunk. If we can solve the silt problem, it's really going to open up the ability for us to capture more stormwater. If we can desilt the stormwater before it hits a basin, then we'll be able to increase the overall percolative capacity of our system. Clogging is that key constraint. Recharge with GWRS or MET water are 2 to 3 times greater than the Santa Ana River water. So we have this blend of water. Pre-treatment of the Santa Ana River water with cloth and river bed filtration is being tested. And new land, of course, as I mentioned, must be considered when available. So that ends my presentation. Thank you very much for your attention.